I mentioned in the first video of this module that in the experiment, the research participants saw rings of different eccentricities. And so we're now going to start exploring that experiment design. What you see here is a visualization of what's called the design matrix in statistics. So the columns here correspond to regressors or independent variables. In our case, that's the 6 different stimuli, the 6 different rings. And the rows, or the y-axis, corresponds to time in the experiment. So the way to interpret this matrix is that each white bar here corresponds to a time point in the experiment when that particular stimulus was shown. Now, this is a pretty good way to visualize the entire design matrix, but I want to make another visualization, partly to make sure that this is really clear. And it's also just an excuse to do a little bit more data visualization in MATLAB. So what you see here is the time course of bold activity from one voxel, and these pink dashed vertical lines show the onset of each stimulus. This is just from condition 1, so this corresponds to the first column here. Each horizontal white bar here corresponds to a vertical pink bar over here. And basically this just shows when that condition appeared over time relative to the ongoing bold activity. Now, in real fMRI data analysis, this entire design matrix gets mapped onto this time course from this voxel. That's done using a general linear model after convolving this design matrix with a hemodynamic response, which accounts for the sluggish bold response that I talked about in the first video of this module. So that's the way that the analyses are done in practice. Here, in the interest of teaching about MATLAB coding, we're going to explore the data in a slightly different way, and that's going to help us learn about indexing and for loops. So what we are going to do is cut out data segments of the time courses surrounding each of these stimulus onsets. So we're going to cut out a segment of data here, cut out a segment of data here, like here, and so on around each stimulus onset. So then we can call each of these stimulus onsets like a local time zero, and that's going to allow us to create a matrix of event-related bold responses that are time-locked to each stimulus onset. So in this image, x-axis is time, but this is not the total experiment time. This is up to 15 seconds after the stimulus onset. And the y-axis here corresponds to voxels, but it's space, but it's not space laid out in the flat map. This is the vectorized version of the voxels. Okay, and then the color corresponds to the percent change averaged across all of the trials or the stimulus repetitions. Now, if it's still not entirely clear what this image shows, then don't worry, I believe it will become clear as we work through the code, and you can see mechanistically how this matrix is created. All right, let's now switch to MATLAB and start coding. We are going to be working with the design matrix. You might remember that there is a variable in this mat file called design. Let's have a look at what we have here. So we have, where is it here? So a variable called design, you can see it's the same size as data in the sense that it's a 1x4 cell array. Of course, in terms of the total memory, it's much smaller. So let's see what's in this design matrix. So I'm going to type design. We can see it has 4 cells, and each cell has a matrix of the same size, and that size is time points by 6, and that corresponds to the conditions. So I actually want to start visualizing this design matrix by plotting it as lines. And basically that's going to motivate the switch to visualizing the design matrix as an image. So we want to plot time, we have this variable time that we created, by design. Now, we cannot directly plot a cell array like this. MATLAB doesn't know what to do with this. So we just pick one of the 4 runs. Let's just go with run 1. And then we can plot a line of this. So now each color, each line here corresponds to the onsets over time of each stimulus category. So, you know, this is correct. This is an accurate depiction of the experiment design, but it's hard to visualize. And that's really why we switched to visualizing this as an image. Okay, so let's just put the design matrix, again, just from the first run, and into the image sc function. Now, it's typical when viewing these design matrices to have them as black and white because the variables are generally 1 or 0. Of course, after you convolve this with a hemodynamic response, it will take on more values than that. Nonetheless, we're going to switch the color map to gray. This is the typical way of viewing a design matrix. Okay, very nice. So now we're going to make that other plot where we have all of the events plotted as vertical dashed lines on top of the time course of a bold response. So let's see, we want to plot the data from, of course, we're just, it's just for visualization. So we're working just in one run, and we'll plot the data from the same voxel that we've been using in the previous videos. And yeah, of course, you can change that if you like. Okay, so the next thing we want to do is find all of the time points that have an event for a particular condition. In other words, we want to find what time point or what time index is there an event here, what time index is there an event here, 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 and so on. So we use the find command and we input the vector that we want, so design from run 1, all of the time points and just the first condition. So this is going to return a list of all of the time indices where that particular condition occurred. So you can see that there's 12 numbers here, and that means that there were 12 presentations of stimulus 1 in run 1. So 12 of these horizontal bars over here. Okay, so then let's see, let's go back to this plot. We are going to generate a plot at each of these event onsets. So we're looping over the event onsets, and it looks like we're going across the entire y-axis. So this returns the y-axis limit. So the y-axis for this plot goes from -15 to +20. So we're going to plot a line that goes from this x-axis value and these y-axis values, and the m dash dash gives us a magenta dashed line. Curiously enough, we don't see any vertical lines here. What's going on? Let's see if we can figure this out by looking at what's inside this plot function here. So remember, to draw a line, which is what we want to do, we need to specify 2 points for the line, the starting and stopping points on the x-axis and the starting and stopping points on the y-axis. So we've already figured out that we get a start and stop point here on the y-axis. However, here on the x-axis, we only have one number. So we cannot draw a line with only one number. So we need to have 2 numbers here. And what are those 2 numbers? Well, the line is actually vertical on the x. It's vertical, so it doesn't move on the x-axis. So what I'm going to do is write 1 times, and then this single number that we want. So the 1 here is, these are just placeholders. This is going to repeat this number twice, like this. Okay, now let's try this again. And voila, we get this very nice plot that we saw earlier. Now just note that this is time on the x-axis, this is time in TRs, in indices, not in seconds. Of course, in this particular case, because we happen to have a TR of 1, this also corresponds to seconds, but I wanted to mention that explicitly because if you're working with data that has a TR of something other than 1, then you would want to convert this into time in seconds. Okay, very nice. So now that we have our visualization, what we want to do is cut data out. So we want to zoom into the data here, and we want to cut out each of these time segments here. So from the stimulus onset -2 seconds and then +15 seconds. And we want to repeat this segmenting or cutting for each of the 12 events in this run, and then also for all the other runs. So before worrying about fixing the code here, I want to have a look over this cell and see if we can get the bird's eye view of what's going to happen in this cell. So we define our time boundaries. This is going to be -2 to +15. We're going to need to initialize a matrix. Here we get a hint for how we want to initialize it. So it's going to be conditions by voxels by time points. And the matrix is called ER bold for event related bold matrix. So then we're going to loop over all the conditions, and we loop over all 4 runs, and then we find all of the events for this particular run and this particular condition. This we just did a moment ago. And then let's have a look at what this is doing. So here we want to grab the data from this particular run around this particular event. So this is where the data segmenting actually happens. And then we're summing up a bunch of things here. So that's why we when we add it to the data matrix, we divide by EI, which corresponds to the number of events, so the number of stimulus repetitions. Okay, so now, yeah, and then I'll talk about this in a moment, but this is basically just dividing because we're doing a lot of summing, so we want to divide to get the average. So I hope that this all makes sense from a conceptual level. Let's start going through it mechanistically and make sure we get all of the lines to be correct. So here we're defining a time vector. Now this has to be a smaller time vector than for the entire experiment run, because this is just going to go from time bounds 1 to time bounds 2. And now we want to convert this into seconds to facilitate interpretation. So like when we created the full time vector, we need to divide this by the sampling rate, which is 1 over the TR. Again, in this particular case, that happens to be unnecessary, but you know, it's good form to keep that in there anyway. Okay, so then let's initialize our matrix. So we have 6 conditions. The number of voxels, remember we created a variable in a couple of videos ago that encoded the number of voxels we have in total. And then we have time. And again, this is the local time here. So we're going to say, or the event related time, the length of time vec. So now we have our matrix that's going to store all of the event related bold responses for every condition and for all of the voxels. Okay, so let's start our loop. Now, when running through code inside a loop, one thing you can do to make sure that you can run it line by line is to initialize these looping index variables just to be the first element. So I'm going to set con_i, so the looping index variable for a condition to be 1, and then run_i also to be 1. And that allows me to basically run the inside of this for loop line by line. Okay, so this part should work. We've already seen a line of code like this before. Okay, now this looks pretty confusing. Let's see what we want to do. Extract the peri-event time series. So that's this here. We want to extract this time series here and store it as a temporary variable. So we're initializing a little variable here, and this is voxels by time. And then we loop over all of the events that we have. So for the first event, and what do we want to do? Well, what we want to do is extract the data from all the voxels and the time in which that event occurred, that stimulus appeared. So let's see, we want all of the voxels, and then we want the events and the EIth event. Now what this is doing is just grabbing the data time point exactly right here. So exactly the time when that event occurred. So we're getting somewhere. This is not yet what we want. Instead, we want to go from this point backwards in time, so 2 time steps backwards, and then 15 time steps forwards. And I'm going to, instead of hard coding this to be -2, I'm going to say plus time bounds, the first element, through events EI, plus time bounds, and then the second element. So now let me dump this code out just to make sure that this is clear. So what we are doing is accessing these time points from the experiment data matrix. So we have this big matrix data, and we're going to get all of the voxels and not all 368 time points. We're only going to extract time points 71 through 88. And that corresponds to this event here. You can see it exactly right here, -2 TRs plus 15 TRs. All right, so this is going to create a small sub-matrix that just contains the data around each event. And now in this case, so it's voxels by time, and we are summing over all of the different events. So how many events were there? There were 12 events. So we sum up over 12 events. So therefore we need to divide by the number of events, and that gives us the average. So we're summing up, dividing by n, that's the average, and then we're adding it onto this event-related bold matrix for this particular condition, and all the voxels, and this corresponds to time points. Now, this here is a 2-dimensional matrix, and ER bold is a 3-dimensional matrix. So in order to be able to add a 2-dimensional matrix to a 3-dimensional matrix within, that only has one element here, we're going to squeeze out that singleton dimension, and this turns this, so the squeeze function will turn this from a 3-dimensional matrix into a 2-dimensional matrix, and that's how we can add these together. Whew, that's quite a lot of code. You can see that, even relatively simple things that you want to do in MATLAB can start getting pretty hairy, but I hope that this all made sense. I think this was really the most difficult line of code here. Okay, now notice what's happening inside this double for loop. So we're looping over conditions and looping over runs. Now, every run contains data from every condition. So therefore, when we're summing, we have to also account for the fact that we are summing up over the 4 runs. And that's why we have to divide by the number of runs over here. Okay, so let's run all of this code. I hope that it all works and I haven't made any errors. Okay, very nice. So we don't get any red text, we don't get any error messages or warning messages. So now let's move on to visualizing this matrix. So we make a new figure and let's just see if this code runs. Oops, we said unrecognized function or variable, image CS. This is a typo that I see made very, very often. In fact, it's image SC. In fact, what's going on is the MATLAB function is called image, and there's another function called SC, and the SC is for scaling. And this means that MATLAB is going to basically call the image function, but change the color scaling so it's adaptive for whatever is the input that you're putting in. Okay, so let's run this. So we get something, but it's kind of hard to visualize. There's a couple of differences between what I showed in the slide and what we have here. For one thing, in the slide I used color map jet, so I'm going to change the color map to jet. However, it still doesn't look right. And in fact, the colors look kind of off. So I'm going to see what color range MATLAB automatically calculated using image scaling. So let's type get current axis clim for color limit. And you can see there's a non-symmetric color axis. So it goes from -28 to +20. It's often easier to interpret images when the color limits are symmetric. So when it would be, -20 to +20. So therefore, this is what this comment says here. So let's see, I'm going to write set get current axis clim. And the way that I often set this up to make sure that we have a symmetric color limit is I'll say -1 +1. So I'm just creating this small vector. And then I can modulate that by some scalar. So let's try maybe 15. Let's see what that looks like. Okay, so it's looking a little bit better, but I think it's still a little bit difficult to visualize. Let's try a smaller scalar. And actually, maybe we'll just leave it as 1 to 1. Ooh, no, that's too much. That's hard to see. Okay, I forget exactly what scalar I used when I was making the plot that I showed in the slides, but this is pretty close. Okay, so that is looking better in terms of the color and the interpretability. However, this here is not the right time axis. We want to have the seconds relative to the stimulus onset on the x-axis. So we started extracting these data at -2. So the solution is actually just to say time vec, comma, and then we need to specify the y-axis variable, which we can actually just leave as empty because, well, we just want to leave this as voxel index. So let's try running this code again. And now this is looking better. So this is time 0. This is exactly when the stimulus occurred. And then you see over all the voxels, there is a change in bold activity. In this case, it looks like most voxels are suppressed. Most voxels have a relatively decreased bold response, and some voxels are increased. And this is just for one condition. This is for the first condition. In the next video, we're going to start exploring this for all of the conditions, as well as mapping this onto two-dimensional space so it's easier to interpret anatomically. The last thing I want to do in this video is get back to this issue of changing the aspect ratio using the axis image. So let's type axis image and see if that makes the plot look nicer. Uh-oh, I don't think this makes the plot look nicer. In fact, it makes the plot collapse into a line. It looks like this is just 1 pixel wide here. Now, what is going on here? What's the deal? Well, remember that, let me set the axis back to normal. So here we have a matrix that is 18 elements wide and 10 to the 5 elements tall. So there's like many orders of magnitude more rows than there are columns. So when we type axis image, what's actually happening is that the aspect ratio is equalized, which means that all the pixels have exactly the same size. Now for this matrix, that's obviously not the right thing to do, but I just wanted to leave it in here as a reminder and to continue the discussion of setting the aspect ratio of images in MATLAB.